Now we're up to the primary function of the topographer, which is the topographic maps. We're going to be doing some topographic maps. Why don't we get straight into it, do an acquisition, and then follow me on the screen and we'll see what we can do with it. What I would appreciate is that these tests should be done without light. Okay, so now we have the patient in the headrest. We've made certain that the eye is in the correct position. Open your eyes wide, please. And what we're trying to do is we're trying to get that center dot in the middle of the crosshairs. And then we're going to move it slightly back. As soon as I see that the placido is slightly out of focus, I can stop. Okay, Liz, I want you to blink once or twice and then open wide as possible. Wide, 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 wide. Great, just keep looking like that. Okay, and we're going to do it again. Like I said, 3 readings. Wide, 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 wide. That's fantastic. Just keep it up, keep it up. That's great. Absolutely fantastic. And I've moved it slightly backwards, and we're going to do the same again. Keep it open, 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 open. Great, great, great. Thank you. We now move to the other eye, and we're going to repeat the process. You'll notice on the screen that automatically 3 images have been saved. And we're going to do the same on this side. So here we're going slightly out of focus. Click once on the joystick and go forward. If we don't go back too far out of focus, then obviously the acquisition's much faster because we're not really moving much of the focus. Most of the problems that people have is that they tend to go out of focus too much. What we'll do now is we'll double click on this image and we're going to get the editing image. And we can see here that the rings, both sides of the rings have been very well caught, 24 rings. We can edit, editing the pupil, basically we've never had to do before. Editing the limbus also not, it's very accurate in the way that it detects the limbus and the pupil. As well as the rings don't really need to be edited if the eye was open properly. So let's click OK. And we can then get on. You'll notice that we have various options here. Okay, we're seeing a tangential image, a sagittal image, a refractive power image, and an elevation image. But we have a lot of options, so why don't we go straight to the options and have a look at what we've got. So in the options, we've got the coordinate systems. We can run polar or Cartesian. We can have cylinder notation, positive or minus. The curvature measurement, we can have diopters and we can also have millimeters. So we can choose which we want. For the asphericity, most countries are using the small e for eccentricity. Sometimes in America you might want to use the p-value, and you can just move that across to the p-value if that's what you want. So here you have the option of the P, the E, the large E, and the Q. You choose what you want. For the scales, it's very important that we can choose between the American style or the Claes-Wilson style. The Claes-Wilson style is used a lot in Europe. Some places in America prefer the American style. The only difference really is the colors. So the colors have changed quite dramatically between the 2 scales. Okay, anterior curvature. So what we're looking here is we can set it to whatever value we wish to set it. 1 diopter, half diopter, quarter diopter, 1.5 diopter. I recommend that we put a small v in here, and I'll show you why that's important later. The elevations, we can run at 10 microns, we can go down to 5 microns if that's important. And the anterior refractive power, we can leave it at 1.5 diopters. That's basically going to give us the scales that we're running at. So these are all items that can be changed by the person who's running the system. You'll notice that all of these maps now are absolute maps. So we're looking at an image that is an absolute map, and we can see that the product on a sagittal map is going from 25 diopters up to 59 diopters. That is the total range that this product can do. You might remember that we put in on the scales the V, which will make that map become normalized. That will only become normalized when we see it as a single map. These maps cannot be changed. There is no way for us to change these original maps. These maps are going to be like this always. On the right-hand side, we have the patient's birth date, the identification code, the acquisition time and date, the group. We also have what's called acquisition quality. We have the centration information. These graphs that are going horizontally are graphs that are normally age-related. If they're in the black portion of the graph is in the green, it's normal. If it's in the yellow, it's suspect. And if it's in the pink, then it's not good. So we can see here that we had a pretty good centration and coverage. We're going to see the summary index. It's going to give us automatically the horizontal visible iris diameter, limbus to limbus, the pupil, the position of the pupil in relation to the geometric center, and the size of the pupil that we did the examination, which was at 3 millimeters. The next set of readings that we've got are the K readings. Now, with the K readings, we have a lot of options. We can go to what's called simulated K readings, which is going to give us only the center area, and we're going to get one value. We're going to get the central reading only. If we go to meridians, it becomes more interesting because we then take one reading at 3 millimeter, another reading at 5 millimeter, and another reading at 7 millimeters. This is very interesting because very often we will find people with an irregular cornea, and the axis and the cylinder can change when we go from 3 millimeters to 7 millimeters, and this is quite important for their refraction. So we can see on this particular patient that we started off with a corneal cylinder of about 1.6, went down to 1.29, and went back up to 1.38. But it's pretty stable, and we're looking at the axes are very, very stable, 77, 75, 73. Meridians are going to give us the K1 and the K2, so the flattest and the steepest. The next option we've got is emimeridians. Emimeridians are now the actual minimum flattest and the minimum steepest values that we have, and we will notice that there are now 4 values on the screen. Before we had 2 values, we've now got 4 values. Okay, and we can see the change. So if we go back to meridians, then you'll see you only have 2 sets of values because it's at 90 degrees. The emimeridians, there is no 90 degrees. It is what it is. They take them at the actual true value of the minimum, the flattest and the steepest values at 3, 5, and 7 millimeters. We also have peripheral degrees, and peripheral degrees are shown as curvature and as sphericity. As sphericity, we're looking from 6 to 8 millimeters, nasally, temporal, inferior, superior, and the average. And what we're going to use this information for is mainly for if they're going to fit ortho K lenses, they might want to use that for the reverse geometry. Then we have shape indexes. Shape indexes, we can choose what diameter that we want to have as a reading, and we will get a single E value for that area. So we could change from, let's say, 3 millimeters and then have one here at 6 millimeters, and we can see the change in the E value. We can get a LSA, the longitudinal spherical aberration. It's giving us the E value and the LSA value. The irregularity of curvature we can see. and the surface asymmetry index. And we can see that the surface asymmetry index is slightly out from the normal. That's why we get this little triangle telling us as a warning. We've also got a automatic keratoconus screening, and this uses what they call artificial intelligence to work it out. We look at the symmetry index, the BCV, which is their formula that they are using to calculate if there is in fact an ectasia and if there is keratoconus. And here we have the radius best fit, and the class here is normal. On all of these subheadings, we have what is called a question mark. If we click on the question mark, it's going to open up the software manual, and it will give us a complete explanation of that particular part that we were looking at. So it's very easy. You don't need to have a separate manual. Everything is written. The BCV, we can see this is the actual calculation that they're running, and they basically are running it based on Seneca's decomposition of altimetry. So we can see over here that the BCV, and here is the actual calculation that they are doing. You can do it as well if you want to. The classifications that we get on the system is normal, suspect keratoconus, keratoconus, abnormal, or treated. So this is a very easy and nice explanation that we can have, and if we go to shape indexes, we get it as well. So wherever we have a question mark, we're going to get that as an option. So here we have the user interface. This is your interface that you're going to be using. We can have a look at the keratoscopy. So here we're looking at a Placido disc, and we're going to look and see that the cross and the dot are very close to each other. If this crosshair is out of the central ring, then you definitely have to do the reading again. If not, if it's very close to the central ring, then we did good. The next option that we're going to have is a single map. Now you'll notice that the scale has changed dramatically because of the V that we put in on the options, on the scales. It has made this a normalized map automatically. If we take the V out, it will go back and be an absolute map. But to get a little bit more information, we prefer to make it a normalized map, and we can see more information. And we see quite a good bow tie effect here. We can see that we've got astigmatism, and we can see the angle of the astigmatism, and everything is going to be shown. So we can see that very, very clearly, the 1.5 diopters of astigmatism. The scale now has changed from 40 to 48, so it's only 8.5 diopter scale, where before we had 22 to, what was it exactly, 22 to 59, 25 to 59, so it's a big difference in the scale. So now we're going to look at the different types of maps that we can get, and we'll do each one separately so that we can look at each one in more detail. The first map that is available to us is going to be the Tangental Map. So here we can see a typical Tangental Map, and some people might know this as an instantaneous map. That was one of the terms that was used to describe tangential in the past. So here we look at the Sagittal Map. The Sagittal Map was known once as an axial map many years ago, and a lot of people prefer this to the tangential because there's slightly less information, and it's a broader version of what we're looking at. We then have an elevation map. The elevation map is going to show us the elevation of the actual cornea. And we can see that in the center it's very, very flat, and then we suddenly get these two areas where it goes down. One of the features of this program is that if we do a right click, we get a tool and we can get a chart, and we can actually have a look at the maps in a chart format. So some people might like to look at it in a chart format. These are the two K readings, the blue and the red, and that is possible to do as well. So we can go back to a cursor, and that's one of the options that we've got. If we go to refractive power, we're going to see what the power is at all the different areas on the cornea. And we can see here that we have a slight difference between 45 and 46 diopters. It's about 1.5 diopters different. If we wanted to, we could actually choose another tool called the gradient tool, and we can click at the top and we can drag it to the bottom and then click again. We will see what the power was at the top, 4495 diopters, the power at the bottom, 4696, and we get a gradient of 0.48 diopters per millimeter. So this is quite interesting if we want to use it on a keratoconus patient. On a patient like this, there's no real value to be using it, but it's one of the features that we've got with the system. We then have a Gaussian curvature map. The Gaussian curvature map is used when we are going to look at a keratoconus patient. And what it does is it takes out the cylinder, and we're looking basically or only at the spherical changes. So it's a rather strange looking map, but it's very important when we use it in conjunction with somebody who has got keratoconus, which is not the situation that we have at the moment. So those are the 5 maps that are available: tangential, sagittal, elevation, refractive power, and Gaussian curvature. If we go to the sagittal map, the next option we have is a 3D map. It's a little bit exaggerated, and we can grab it with the mouse and we can rotate it. So it's easy to rotate this image and to see what the actual cornea looks like. It looks like very what we saw earlier when we had a look at the elevation. We can see that in the center it's rather flattened and it's got the 2 indentations on each side. This is a little bit exaggerated, but that's what the map is about. What we're going to look at now is we're going to look at a keratoconus patient so that we can see what it looks like, which is slightly different to a normal patient. And if we go into the modules, we'll see tangential, sagittal, refractive power, elevations. And at the bottom, it's going to tell us that we've got a person that is keratoconus compatible. The most important thing when it says keratoconus compatible is that there is an area. If there is no area shown, then it in actual fact is not keratoconus, and it's a little bit confused. The Symmetry Index, if we look at it, is way in the red and has a red triangle. The BCV has a red triangle and it has a broken scale showing us that it's really, really bad. Then we have the radius best fit, which is 608, which is not normal for this age, and then we have the RMS value. So this is telling us that we are keratoconus compatible. So what we can do is we can go into the next icon, which is a keratoconus screen summary. On this, we're going to be looking at a map that is tangential, the Gaussian curvature that I spoke about earlier, and elevations. So what we're looking at is we are looking at the part that is the highest curvature, and with the elevations we're looking at the peak of the ectasia, the highest level that we have on this cornea. And if we look at the difference between the tangential map and the Gaussian curvature map, you'll see that there's almost like a cylinder here, where we don't have that here. The cylinder value has been taken out, and we're only looking at the actual spherical map. Now, what we're going to see on the final map is we have a white area. This is the actual area of the keratoconus, and we can see that the two icons, the first one being the X, which is coming from the tangential, and then the little plus sign, which is coming from the elevation. The closer that these two are together, the stronger the effect of the keratoconus. So what we can see here is a typical keratoconus patient, and we can actually see where the keratoconus is taking place. We can also see it over here. So on the elevation we can see it, and as I'm moving the mouse you can notice that on the tangential and the Gaussian map it is also showing the area where it is. What's interesting is that we can see that this keratoconus is basically in the center of the pupil, and we'll be able to look at some other maps which will make it quite interesting to see the effect that the patient has who has got keratoconus, and we're going to be doing that in a few maps time. What we're going to look at now is we're going to look at this particular map. This map is going to show us the altimetric, which is the height map, and we can see that over here we have a big difference in the height. If you have a look at this area of the screen, you're going to notice that wherever the mouse is, it's going to give us a value. So we can see that the value here we have a value of minus 12, minus 29, minus 83, and here we're going into a value of 0. So this is the highest point. This is what they've taken as a 0 value, and we can see that there is quite a steep ectasia here, so we can actually see it happening. These are the higher order aberrations, and on the Seneca we can actually take out certain values, and we can see how the map will change, and if you want to you can put them back in. So here's all your higher order Seneca values, and we can change them. We can also use a reference surface. We can have spherical, we can have aspherical, and we can have a spherotoric. So we have different values that we can actually use for this. So a lot of people would like to use spherical values, and then you can change the diameter and you can change the RF value. So this is basically a height map that is slightly more detailed than what we would get from a normal height map. Again, we can go into the tools, we can do a chart, and we can see what is going on. So we can see how the actual ectasia is on a steep upward slope. Okay, what we're going to be doing is we're going to leave this map. Okay, so what we're going to now move, we're going to move to this black and white image. We have a little arrow. We click on the arrow and it's going to give us a drop-down menu. So we have Seneca Summary and we have Optical Quality. The Optical Quality is very interesting because here we have different maps, and we can go into a wavefront map instead of a, let's go into American style. So what we're looking at here is we have a wavefront map. We have the associated theoretical vision that the patient will have, and we can change this from an ETDRS to a Siemens star. We can turn it into Charles Allen Gilbert with his lady looking into the mirror that converts into a skull. But let's leave it as this. So this is kind of like we're sitting inside the person and we're actually seeing how they are able to see. This over here at the bottom is the PSF, the point spread function map, and here we can actually see the distortion that is happening on the cornea itself. When a point of light hits the cornea, we can see how it's becoming distorted. What's interesting is, let's go to a very small pupil, a 2 millimeter pupil, and we'll see that we have here a very high cylindrical value being shown. The point spread function is not wonderful, and we can see that the patient's vision isn't good at all. Here is a theoretical prescription that theoretically what the patient would need. And again, we have astigmatism, defocus, all of the Seneca triangle information in front of us as well. What we can do now is we can say, that's great, this is how the patient sees theoretically through a 2 millimeter pupil. Let's see what happens at night with this patient through a 6 millimeter pupil. In other words, what we're doing now is we're measuring 6 millimeters of the cornea versus 2 millimeters that we had earlier, and we can see that the point spread function is far greater, the distortion is much worse, and of course his vision has changed dramatically. The MTF has also changed, but this kind of like gives us an idea to understand what's happening with the patient. The patient has halos, he's seeing stars, and all the good things that are happening because of the keratoconus with this patient. The keratoconus was really centered very much over the center of the pupil and has created this very low vision that the patient has got. This map over here is the MTF over frequency, and we can see that that's not normal at all. On the same icon, we can have a look at the Seneca Summary. So when we look at the Seneca Summary, we can see the astigmatism on the first map. We can see the comma, the spherical aberration, the residual aberration, the higher order aberration, and of course the wavefront. We can convert from wavefront to OPD, optical path, and it's going to basically flip it by 90 degrees. So the choice is yours how you want the representation. What's important here is, again, we can change it. This is through a very small pupil, a 2 millimeter pupil. It says so right here, and we can go through a 6 millimeter, and we can see the distortion is much, much worse. Here we can really see how the cylinder is. Here we can see the comma, how it is, the spherical aberration, the higher order aberration. So this is not a happy patient. Here in the right hand corner we have all Seneca values, and we can see that very few of them are in the green, most of them are in the yellow or the red. So here we have all the values laid out for us so we can see them very, very easily. This is a very nice map to look at. A lot of people use the Optical Quality summary to be able to understand what the patient is going through and to empathize with the patient. And it's a very easy way of understanding how the patient is actually seeing. What we'll look at now is this icon, which is the green icon. The green icon is basically the contact lens fitting. It actually asks us on this particular patient, do you want to use keratoconus lenses? Yes, we want to use keratoconus lenses. Select a manufacturer. Gaussian, a manufacturer that manufactures keratoconus lenses. We have a list here of a lot of American companies, Arcadia, Escon, Bausch Vision. So there's quite a range of lens manufacturers here with their product, but I know that Gaussian manufactures for keratoconus, and it's given us a theoretical fluorescein pattern of what this lens will fit on the eye, and we can see how it's going to be fitting. We can change the diameter and see what happens, and we can change the base curve. So if we change the base curve a lot, we can see that's not going to do it. We go another direction, that's not going to do it, we're getting a good touch. So this is mainly going to be for people that are fitting contact lenses. It's going to be kind of like a free person to give you advice on what lens to first start with, and we can rotate it, and we can have a look at this graph in all different at all different angles, and get an idea of what lens we might want to start with. We also have an option with the hand tool to be able to move the lens. Now we cannot move it that it becomes red, because then it's out of the eye, but we can move it up and down, and we can see the effect that we will get with this lens if it moves. So that's a nice effect that we can see, where we can see what's going to happen with the actual lens. Normally we'd want a lens to have about a 20 micron tear film thickness, but obviously with a keratoconus lens it's going to be higher than that. So this basically allows us, without putting a lens on the patient, to get an idea what the actual fluorescein pattern would look like. We don't want to spend too much time on the autofit, but it will work with normal lenses with normal eyes as well. Right, what we're going to do now is we're going to talk about follow-ups and how we can have a look at different exams that were taken. We'll take this particular patient and let's have a look at what we've got. What we can do is we'll go into a single map, and here we have various options for the follow-up. We can do a comparison, we can do a differential, and the difference between a comparison and a differential is very simple. The comparison allows us to look at the two maps side by side, and the differential will take the one map away from the other and give us the difference between them. So let's do this. It opens up a window and it says patient management. So if we go into the patient management, we can see that there are two keratoscope maps that were taken on the same day at different times. And we have a right eye. So what we can do is we can go to the second one, and we can simply drag one of the maps across. If we had more options here, like 6 months ago and 6 months before that, we can drag up to 3 or 4 different maps into this, and it will do the comparison for us. So if we click OK now, it's going to automatically show us the two maps, one on top of each other, and we can see sagittal, sagittal, and we have the same information that we've had on all of them. So we can see the first one, which was done at 11:01, and the other one that was done at 14:21. Okay, the times are shown, number 1 and number 2, so we can see that the maps are very, very similar. This map that we're looking at the top was shown not as a normalized map, it was shown as an absolute map, and that is why we have a difference in the color, but we can actually see that it is very, very similar. If we go into the differential and we do the exact same, we can see now that we have the first map, the second map, and this is the difference between the two maps. So the only difference that happened here was that we had lunch in between, and we can see that they're very, very similar. There's no real big difference. And we can have a look at it. The indexes refer to either acquisition 1 or acquisition 2. So that's going to be that. On the wavefront comparison, we can do the exact same test, and we're going to look here at the wavefront between them. So here's the wavefront, and here's the higher order aberrations, and we'll get the two together. The wavefront differential is going to be exactly the same, and we're going to get test 1, test 2, and then the actual differences between the two tests. If we look at these two tests, they look pretty similar. Okay. So that goes as far as the comparison. We can also do a comparison of right eye versus left eye. And we can see here the right eye and the left eye. You can see that they're quite different on this particular patient. We cannot do that as a differential. We cannot do that on a wavefront comparison. And we cannot do that on the wavefront differential. This internal component is not really functional if we don't have an aberrometer, because we would need an aberrometer to get the information, a true aberrometer that will allow us to combine tests from the topographer and the real aberrometer together. So that's not actually going to be something that is going to work. We can look at these maps, of course, tangential, sagittal, elevations. It doesn't matter how you want to do it. You've got the ability to look at these maps with all those options. Thank you very much for your attention.